All right, so yeah, my name is Mohamed. I'm CEO and co-founder of a startup called Kolena. We're building testing and debugging platform. Now, I'm not going to be talking about Kolena here. We're talking about our learnings from the process of building testing infrastructure for other teams. And then we have our product now is building testing platform. So in this chat, we will share our learnings on how to build rigorous testing infrastructure in our organizations and how that yields into building a culture of quality for our teams and systematic testing for our models. Quick intro, Zohaib did a great job in introducing me, so I'll just be brief here. So yeah, co-founder of Kolena, author of Manning's book, Deep Learning for Vision Systems. Previously led AI teams at Amazon, Twilio, and Synapse, was acquired by Palantir. What Zohaib did not mention is I have been burned a lot by model failure incidents. I'm not very proud of it, but my only consolation is I'm assuming a lot of you folks here have had your fair share of embarrassing situations demoing your ML products, talking to customers, trying to set their expectations on what is working well, what's not working. And that's what led us to start thinking and researching about what's the best way to test our models and how we can scale that within our organization. So if an engineer is testing, another engineer in different organizations is testing, they are all getting the same results in a systematic way. A little bit setting expectations. So I'm not here to push processes on people or try to push different specific ways of doing things, but we're rather trying to start these conversations with the ML community on what we've learned about building testing infrastructure for machine learning and how we can start thinking about building rigorous testing platforms or architecture for our ML models and shipping our models with confidence. We want to be able to understand what are our failure modes every time we run a test, how we can track them much faster than the way we're doing this now. Today, the only way of trying to identify what the failure modes of our models is trying to go through our data points, whether they're images or even harder videos or LiDAR, trying to look at every data point to understand where our failure modes are happening, which is a very tedious process to go through. How we can run systematic model unit testing, regression testing, integration testing. All these processes that have been borrowed from the software side, they're working very well, probably much better from our experience on the machine learning side, given the right infrastructure that you can build in your organization. How we can intuitively communicate the performance of our ML products with our customers to set their expectations with our teams, with the leadership. This is a part that I can claim with a high level of certainty that it's a pain in every data scientist or machine learning role that trying to build a model, and then we have to talk to teams and tell them, my model is 99% accurate. Which is funny part that machine learning engineers try to be politically correct or statistically correct. We never like to say 100%. So the new 99 is the new 100% now, which is like, hey, I'm not wrong, but my model is perfect. Last thing here is teams are building products. They spend months, years, learning new edge cases. All this knowledge base is lost. All this knowledge base, when you have a new engineer, we have to spend tons of time to onboard them on what we have learned. So how can we have this infrastructure that we built for testing becomes a knowledge base for all the what's the rubric for our quality here? For every time we're testing, we're increasing our resolution on our model performance. Now, with all this talk out of the way, let's jump into a story from my experience. At some point, we were building weapon detectors in X-ray imagery. And the X-ray machines here, like you guys in airports and other security checkpoints, we went into a customer demoing a model that is 99.5% on recall. Now, if you're familiar with the recall, this means that I'm expecting, as the developer of this model, that I will have one failure every 200 instances of a gun. Pretty impressive. But we end up having one of our customers pull the gun, dropped it in an empty bin, passed it through the X-ray machine. This is how it looks on the screen. I see some smiling faces. See, you know what's coming now next. We actually missed it. So when we end up, as computer vision engineers, when we say my model is 90-something%, we kind of assume that this 1% that's remaining, or 0.5%, is the most adversarial case. But what ends up always happening is the model might have improved in more adversarial cases and regressed in easier cases. You have 99, 99, you don't know if they are the same performance. Now, the problem with that, obviously, you lose the customer trust, whether your customer is internal or external, right? So if you're building for leadership and there's no ROI on your products, you lose their trust. You give into a customer your product, like the gun here, they're not going to talk to you again. They're not going to buy your product. The more embarrassing fact here is we have seen this failure internally in our internal development before, this gun and empty bin case. We've seen that failure before our team. But the problem here is, talk back about the knowledge base or regression test, we did not have this dynamic test harness that's always tracking these edge cases, running regression tests every time I'm improving my model. I want to make sure that the bug I caught 3 months ago, I am catching now that I'm not regressing. When we started researching this problem, we wanted to take a look at how machine learning engineers, specifically computer vision, are testing their models today. Now, across the industry, the process is we set some test data aside, and then we run inferences on a trained model, and then we stare at some error charts for days or weeks, and then we look at all the images, videos, data points, and then we come up with some kind of global metric. I am 99% because I cannot say I'm 100%. So we're 99% in detecting a class, let's call it a car. But it's not clear how the model is doing when the car is in the daytime, nighttime, rain, snow, dust, close, far. Tons of scenarios are abstracted by one metric, and that's what happened to us in the gun scenario. So we end up having to make big decisions. We end up having to make big decisions based on very low resolution results or visibility on how the model is performing. So what happened to us at the time, we went ahead with the V1 of the model, was performing 97% on recall for the gun, and improved to 99%. Now, the mistake we made is we deployed the V2 here. Why? Because this is all the information we have. I mean, at this point, we end up, it's not clear which model is doing better. And then, more importantly, what has improved? We went from 97 to 99%. Did we improve equally in the entire the scenarios that we can represent? What has improved? What has regressed? Which model should I deploy? Or more importantly, is my model now ready to be deployed? Like before 97, we probably were at 93. And then do we deploy now? No, 97. Do we deploy now? We don't know. 99. Do we deploy now? We saw what the 99 happened. So we started seeing a lot of these statistical metrics on the aggregate level don't describe anything really. It's just a percentage of your test data that we don't have much visibility on what this data look like. Last point on the slide, what's our test coverage look like? Isn't this what every time machine learning engineers, they get this question all the time? What have you tested on? Did you test on the data that we put from this site? Did we test on this? Hey, we added edge cases. Hey, remember we failed this? Did you test on that? What's the test coverage? Without the test coverage being very clear for teams, you will not ever be able to build alignment and trust between teams and obviously with customers. So the research community coined the term here, called it hidden certification problem, and describes exactly what we were talking about, that the model exhibits highly variable performance across the different subclasses of this class. And they gave an example here. I can't point. My mouse is not working here, but they gave an example here in their paper that I cited down there of a chest X-ray detector of detecting cancer in chest X-ray imagery. And then you see the curve in the middle, the blue curve, that's the aggregate metric. Now, the aggregate metric is showing some decent performance of the model in detecting cancer. But when the researchers started diving deeper into the results, they found out that the results are being skewed by a very easy class, which is the orange curve right there. And that's the curve that the doctors have chest drains to mark that this patient has cancer. So the model was already cheating. But what actually mattered is that green curve, when the image doesn't have any chest drains, doesn't have any indication that this is a cancer patient, and it's performing very poor. So we end up, their conclusion is the models, that this aggregate metric that we've been relying on for the class does not describe the full picture. Now, the other thing is, if you rely on aggregate metrics, you will end up having to deal with models that are failing and regressing silently. Another problem with this, the way we manage our test data sets, same thing as we're looking at the class, we're not looking at them at a stratified level. You end up having misleading results if your data is not distributed right. I'm talking here specifically about test data. Test data doesn't get enough attention from us as data scientists. We end up having to arbitrarily split 70, 30, 80, 20, whatever. But in this example here, this model is not, I'm looking at the blue curve. The blue curve here is the distribution of the test set across these different scenarios from 1 to F and from A, B to F. And then you see that the subclass D, or scenario D, is not very well represented in my test data. So while the model performance is very poor, which is the red curve in that scenario, your aggregate metric will show that 99%. So paying more attention to our test data is what we're focusing on here. And then the starting point is a paradigm shift from a way we live in now when we have a bulk of data that is labeled by the class, and usually it's arbitrarily split between train test, into a world where we have a fine-grained, well-curated test cases, and which is called in software unit testing. So in the gun example here, instead of having some bunch of data, this is a gun, we want you to stratify that into different scenarios that you care about from your product perspective. Gun and empty bin, which is one we saw before, and then top view, front view, and so on. And then you keep growing your knowledge base based on that. So this low resolution results will turn into high resolution results when you're looking at the test case level, which is a subclass. So you'll notice here that V1 of the model, while performing on the aggregate level has lower performance. But you notice that the gun empty bin was doing very well. I personally should have demoed that model. But you notice that the back view, front view, basic orientations of the gun, the model is performing very well. And then when we as a team try to improve the high occlusion, high blur levels of the model performance, we did improve in the next iteration of the model, but we silently regressed in a very critical piece for our product, which is the gun empty bin. So as a decision maker or as product managers, I have much better visibility on which model is better for this kind of deployment if you're deploying into different sites or different applications. And as a machine learning engineer or a scientist, I know exactly what have regressed in my product, and I'm able to address these regressions one at a time. So back to paying more attention to test data sets. I believe that properly managing our test data is much more important than training data. Test data is, if you're building, obviously, a model, training data is just meant to train the model to generalize for this class or for this problem. So you don't need to represent every single scenario in your training data. That's actually counterintuitive of the concept of machine learning. You would that's what basic programming look like. But what you need to do is you gotta represent your test in every scenario that you're building for in your test data to test for how the model has the model generalized, and then if not, maybe one of the solutions is to represent it in the training data set. So we're looking at the test data. Since I don't have a pointer, so the top here, the ML engineers. ML engineers they use the test data, obviously, to guide their development, understand how the model improves. We all understand that part. But what we want to do is, we want to loop in product managers or customer-facing, the voice of customer, into this process. They need to start encoding their requirements of the product into test cases or unit tests. Another thing is, non-technical teams like biz dev, sales, external customers, they use this test data to communicate and set expectations on what this product does, where it's poor, what has it improved when you give a model, and then a few months after that, you give another model. These questions always come up. So everything happens from the test data. So with that, how do we think about, or what are our thoughts on how we can manage the test data in a different way. So we're borrowing few concepts from software testing. Test case, test suites, nothing is new here. Now, a test case is basically just a test scenario. It's a group of data points, image, video, whatever it is, that have the same characteristic that you want to test, whether it's a car, the day, at night, rain, snow. Actually, another example that, I don't know if I have time, another example that came to mind, because things are not always as straightforward as day, night, and so on. The rotation of the bounding box, the aspect ratio of the bounding box, the size of the bounding box, all these are scenarios, believe it or not. Now, we want you to start thinking about the test data, break it down into test cases, and then group them into test suites. A suite is just a group of test cases, and that makes it easier to manage in our heads. So that benchmark data set on the side will be test cases, scenario A, B, C, and so on. And then test suites. Test suite can be and should be a regression suite. You have a regression suite, and you can have a suite that's, hey, every time you deploy in this location, run these tests. Every time you update the model, run these tests. Teams have different ways of grouping the data as test cases and test suites. But with these two levels of data, a lower level test case, higher level test suite, we've seen teams run tests much, much faster, and the debugging part is super fast because you're not just trying to figure out how the model is doing for every case. You just, with one look, you're able to, okay, my model is dropping performance at night, for example. Now that you've set up your data into test cases and test suites, now start thinking about that knowledge base that we talked about and test coverage, and start building this transparent environment in your organization where everybody knows what you're testing on and what's your rubric look like for quality. And you build your team alignment. So if you have another, let's say you're hiring a new engineer, and then they are asked to, test all my car detectors models. We have hundreds of models. Test them all and find the best model for this deployment. Now, this new scientist that joined the team, they don't need to be onboarded on the years and years of learning on what you have learned, because you have encoded every single case into a test case and build your knowledge base right here. Now, this new engineer will come in, and then let's assume a young engineer just graduated college. All they have to do is run test cases on the test suites that the team has already created. They log in and they see, hey, the team is already paying attention to the car orientation, front view, rear view. I don't know if you guys can read that. Oh, it is. We created 3 test suites for the car. One is the orientations of the car, or the orientation of the car. 2 is the type of the car. And the 3 is the light and weather conditions, like day and night, and rain and snow. And then we can have these conversations with engineers, product managers, customers about the test coverage. Why aren't we testing against foggy situations or dusty situations? Do we need that? Yes, okay, let's go ahead and create these test cases. If we don't need them, then okay, then that's good. We're able to focus on what we need. The cherry on top here is once you have these test cases, you're able to create these behavior report cards where you're able to communicate to non-technical teams or even technical teams the behavior, the expected behavior from your product, even more delightful for customers when you give them an update and you told them, I improved in these scenarios that you were complaining about. But now you can assign these qualitative metrics to your test cases and to, here's the metric I care about, F1 score. I will have good, very good, excellent, and so on. And then I will see that scenario A, D, and E are doing excellent. Scenario B is doing very good. Might be very good, but it has regressed because you see a red button down there or a red arrow. So you get to have more intuitive report cards to manage the performance of your models. Now, regression tests, we've been talking about it for some time, but now we have built the process and infrastructure for that. Now, identifying regressions is not going to be a hard task at this point, and being able to make sure that we do not silently drop in a slice of the performance in our model. Knowledge base, we talked about it as well. I see it as a necessary effort in our path to chasing that long tail. I'm sure you heard that long tail like 10 times today, and you hear it and you read about it in every article. But again, this is the nature of machine learning, is we don't know what's out there, and it never ends. And the only way to chase that is by building this knowledge base. And then support your team with the right infrastructure so that you don't end up being like the person playing whack-a-mole. They squash a bug, like what happened with us with the gun, and then a few months after that, the bug appears again, and then appears again, and so on. Last thing is, we talked about regression tests, unit tests. Now, end-to-end testing. Another thing that teams fall into is the test model. It's doing great. Let's package it, wrap it with pre-processing, post-processing code, throw it out into production. The model changes its performance, obviously, we know that, after it's been packaged in different hardware, after it has its own evaluation logic. So we ran a case study on the JAD dataset. It's the autonomous driving dataset. And then in this case study, they are detecting pedestrians, tracking them, and classifying whether the pedestrian is crossing or not to avoid collision. So in this here, we ran, so obviously there's a pipeline of two models, simpler application, sure, tons of applications that have pipelines of different models. So in here, the tracker, the detector and tracker, we tested on two models. One is called sort, one is called deep sort. And for the classifier, we tested on the C3D and static. Now, when we tested the model individually, we found that the deep sort is a better detector and C3D is a better classifier. But when we tested this end-to-end system, this is like a 2-on-2, so you have 4 possible combinations. So in general, if you test 4 possible combinations in a regular world without unit testing, you will get similar numbers, 94, 93, 92, and it doesn't give clarity on what is better. But now having the right setup, unit tests, regression tests, now we can have higher resolution comparisons, and we found that the winning combination is sort and C3D. Now, when we say winning combination, we have to be aware that for that deployment, because different deployments have different needs, have different unit tests that we care about. So not every combination works for every model or for every system, and not every model works for every problem. That's why we cannot rely on these aggregate metrics. We have to start focusing on what we're building for. Last note, actually perfect on time. I totally understand that building a rigorous process like this is very hard, and setting up these processes is very hard. I believe that building a culture of quality in our organizations is not a heroic one-time effort by some engineer or some manager in the team. It's not a groundbreaking architecture or a neural network. It is a process that you need to systemize, start from the ground up, how the models are being tested, what's the quality criteria, and then everybody's testing on the same thing. So that's why we built Kolena, to make sure that this robust and systematic testing process is available for all computer vision teams, whether you are a handful of engineers or an organization of hundreds of engineers. Thank you, everyone. I left here my information. Please reach out, let's chat. I want to hear more about how you're doing this now. Let's have this conversation with the ML community, see how we can build the right rubric or the right blueprint for a testing infrastructure in our organizations. Thank you.